Hello, chemistry students. So we continue with our gas and atmospheric chemistry unit. We're going to look at several gas laws, not all of them right now because that would take too long, but certainly a few of the main ones. Okay, so let's get started. Okay, our first. Well, I don't have anything listed here, but just think about this. This is a syringe, something you're probably familiar with. Essentially, if you imagine this scenario, if you put your finger at the very end over here, so just block it off, stopper the syringe, right? And that's after you have pulled this part out, right? So this is filled with air. Then you stopper the syringe with your finger just over here. Okay, then once you have pulled out air, you have your finger there. Then if you press down on this end of the syringe, you're gonna feel that you're gonna see the volume is now decreasing. So volume is decreasing, and you're gonna feel the resistance caused by an increase in pressure. Right, you can feel that pressure as you're pressing down on this end, and the volume is decreasing. That's one of the laws we're going to talk about first, and that is Boyle's law. So we'll get into details, but before we do, this is of course explorelearning.com. So we are all now familiar with this. You're going to go to explorelearning.com for this lesson, and I'll have Boyle's law and Charles's law ready for you to go and practice. This is where we're going to get some data from this for this lesson that will help us hopefully understand Boyle's and Charles's law. Okay, now these are just screenshots I took myself from performing those gizmos inside explorelearning.com. So I'm summarizing what you will find yourself when you complete it. This is just an overall summary before we get into the details. So here we see that this graph shows us that if you increase pressure, so here on the x-axis we have pressure, or rather volume. So if you increase volume, what happens to pressure? Well, we start off with a higher pressure and we go lower and lower and lower. So you can see that as you increase volume, you decrease pressure. Okay, so as you increase volume, you decrease pressure. So the opposite would be true too as well, right? You would see that if you decrease pressure, so reading this in the opposite direction, if you decrease pressure, notice volume would increase, right? That syringe thought experiment I referred you to at the very beginning. All right, now for volume and temperature, this is our next law, Charles's law. Volume versus temperature, we see that as you increase temperature, right, increasing temperature going left to right on the x-axis, you see that volume increases. Right, so we'll talk about these details in just a bit, but these are the summaries. This is the summary of our first two gas laws. Okay, so under Boyle's law, now think about this. Hopefully you've had experience at maybe at birthday parties with balloons or anything like that, or just think about what your answer might be in your head. Try to answer these questions before the answer is revealed. So if the pressure doubles, so under Boyle's law, if you double pressure, right? So pressure increases. If you double pressure, so you're squeezing on a ball or a balloon or something like that, or a syringe without again with the same setup, your finger at the end of the syringe, and you're pressing down at it. So if the pressure doubles, the volume decreases by what? This is purely a guess. The volume will decrease by, okay, you're going to finish off that sentence in your head, and it turns out it decreases by 2. So if pressure has doubled, volume has decreased by 2. Now, if you have done the explorelearning.com gizmo, you would have probably come up with this relationship yourself. Okay, and I will in our lesson instructions encourage you to look at explorelearning.com before you listen to watch this lesson. Okay, next. So given this, so if we see that pressure increases by, you've doubled the pressure, turns out your volume will decrease 2 times as well. Now, if the pressure triples, the volume will decrease. What do you think? So given this relationship, you can probably say in your head, you're thinking about the answer right now, the volume decreases by 3 or by a third. Okay, so we're coming up with a mathematical relationship here. This is the idea. Okay, so as the pressure on a gas increases, the volume of the gas decreases. Okay, we've already seen that here and in our thought experiment. What's new is that this happens proportionally, right? So if pressure doubles, volume decreases by that same factor. If pressure triples, volume decreases by that same factor. Now, this part's important to say. We're assuming here that other variables that might affect pressure and volume remain the same. So temperature must be constant, and this part is a bit funny, but if we're considering that there is a change in volume, we can actually cancel this out. So it's just temperature must be constant. Okay. Again, here is that relationship there. Now, what happens is, I should go back. If we plot, as you've already seen previously, if you plot pressure versus volume, you get this. This isn't a straight line. If I had it earlier, here you go. It's not a straight line. It is a curve. Now, we want to come up with, as aspiring mathematicians or scientists, you want to come up with a relationship between pressure and volume that can give you a line. However that line may look, it may look like this, it may look like that, but you want a line. A line tells you is easy to predict, right? Remember back to grade 9, an equation of a line. We're going to take slope into consideration here as well. So you want to come up with some kind of a line that looks like this, but a curve doesn't let you do that so easily. But if you play around with the math for just a bit and you see that, see if I can get rid of here, pointer options, erase all ink. Okay, so look what's happened here. Now we have pressure versus the inverse of volume. So it's not pressure versus volume, it's pressure versus the inverse of volume, 1 over V. Now, why did we do that? Well, because look at the relationship here. This is a straight line. That's a straight line, and that's great because you can come up with, and I probably thought that even after your grade 9 math teacher told you that you would see it again, you probably thought that you would not see this again, and yet here it is. Y is equal to mx plus b, an equation of a line. So remember that this line allows us to come up with an equation, something that is predictable, something that we can plug an x value to get a y value, and that's great. So y is equal to mx plus b, and if you remember what b stands for, right, the y-intercept, x in this case is inverse volume, right? M we know to be our slope, rise over run, y2 minus y1 over x2 minus x1, and y in this case is pressure. Okay, so let's start plugging things in, and here we go. So pressure being our y in this graph, m stands for slope is a constant. It's some constant, right? So we can just write constant. We know that x is 1 over v, and we know that our y-intercept is right here. It's just 0. So let's simplify this, and we get really what you would get is just pressure is equal to constant, some constant, times 1 over v. And if we manipulate this formula, we see that P times V is equal to some constant. Okay. Now, that constant then, if we go back, that constant allows us to derive a formula because that constant will not change. If we take measures at different points, right, volumes and pressures, that constant will be the same. So that allows us to compare one scenario to another. So we can say P1V1 is going to be equal to some constant. Now, if we change P or V, it still will equal that constant. So a second scenario here could be P2V2. Right? A second scenario will be equal to each other, to the first, because they're all equal to the same constant, that same slope, which is essentially Boyle's law. P1V1 is equal to P2V2. Not too difficult to forget, not hard to remember. Okay, and here's our first example. All right, so here it's worked out for you really well. In your initial pressure given 103 kilopascals, right? We're gonna use these units. It does work with other units as well. We're gonna try to stick to the standard SI unit here, as we do in Canada and everywhere else except one or two places in the world. Liters, we're gonna try to stick with liters. Again, other units work, but you'll see when we get to the ideal gas law that units become more important. So let's just try to stick with these units. So 5.2 liters is our first situation, our first scenario, right here. Our second scenario has us at an increased pressure. Look, now we have 400 compared to just over 100. And the question's asking you, what is our second volume? What is the volume in that second scenario? Now, even before you plug things in and work it out, think about what you should expect to get here. It's kind of a self-check, if you will, even before you've done the question. If you've quadrupled roughly, not exactly, but if you've quadrupled pressure, then you should expect your volume to decrease. So if you end up with an answer of, let's say, 10 liters, well, that you know is wrong, because it should actually decrease. Okay, so just plug things in, right? Plug things in. We know P1, we know V1, we know P2, we don't know V2. All right, so a little bit of grade 9 algebra here. Simplify, solve for V2, right, in this way, and you get 1.31 with a standard, not standard, with your sig figs being here. So 1.31 liters. That should make sense, right? You did expect this volume to decrease, right, roughly by 4, and there you go. 1.34 liters is the new volume. Okay, so if we were in class, I would play a short portion of this clip. It's a song that was popular when I was in grade 11. Maybe I'll share that in our class comments, but let's move on. The next law, we saw a preview of the Charles's law, and its relationship, it looks at the relationship between temperature and volume. Yes, that song was called Temperature. Okay, so pencils down for now, we're just going to talk. Okay, so think about these situations here. Now, imagine a balloon, right? Small balloon here. This is liquid nitrogen, very cold liquid nitrogen. This balloon is going to go into the liquid nitrogen, and you would expect, well, what would you expect to happen? So think about that for a second. You probably would expect it to, now you're saying this to yourself, look at that. So it's decreased in volume. So what we can look at here is, as temperature decreases, what happens to volume? Hopefully you're saying it looks like it's also going to decrease. Look, it shrunk. Okay, now let's see something else. Now, what happens if you heat a gas? If you heat a gas, like a hot air balloon, right? A hot air balloon, what the reason it floats is you've decreased, well, you've increased volume by blowing hot air into it, by therefore increasing temperature. Now what's really happening here, a little bit of background, is what's really happening is as you have increased volume, you've also decreased density, because density is mass divided by volume. And if you decrease this, sorry, let me correct that. If you increase volume, right? If you increase volume, this denominator becomes greater and your density therefore becomes smaller. You've decreased density. That allows this balloon to float in the atmosphere, right? Because of this hot air, right? So that's a little background there. Sorry for all that scribbling. Okay. Now, before we can talk about temperature, it's important we look at what temperature and how we measure temperature, and how we can, in this case, compare 20 degrees Celsius to 10 degrees Celsius, or even Fahrenheit for that matter, but we're not going to talk about that. Okay, so here are two questions for you. Is 20 degrees twice as hot as 10 degrees? Now, mathematically, look, it probably makes sense. Look, we have 10 degrees Celsius. If we multiply that by 2, we get 20, right? You learned that in elementary school. So now the question is 20 degrees twice as hot? Okay, also, now that I've asked that, the second question is, is 20 kilograms twice as heavy as 10 kilograms? Again, if you take this number, you multiply it by 2, you get 20. So maybe, but what's the answer? All right, so think about that, and here are the answers. So first, no. Now this is a bad proof for it, I admit, but just it works here. So the answer is no, and an example of why, or reason, is that if you convert 20 degrees Celsius to Fahrenheit, you get 68 degrees Fahrenheit in Celsius. And if that is not then double 50 degrees Fahrenheit, because 50 degrees is Fahrenheit is 10 degrees Celsius. So if it were really double, then you should get 50 times 2, we should get 100 here, and that's not right. So this is a weak proof, I admit. We shouldn't be using Fahrenheit at all, but it does answer the question. The answer is no. Okay, now as for our second question, that the answer to is yes. Yes, so if you do have 20 kilograms, 20 kilograms is twice as heavy as 10 kilograms, right? We convert that to a different set of units, we see that that holds true. 22 pounds is equal to 44 pounds. Okay, so what's the difference? Okay, weights have weight measured. We can get into the physics of this as a result of gravity and all, but we're sticking with the chemistry here. Weight can have a minimum value of 0, right? It can't be a negative 5 pound or negative 10 kilo weight. It has a value, an absolute minimum value of 0. But temperature in Celsius does not, right? Living in Canada, we know that it goes well below 0 degrees Celsius into the negative value, certainly, right? Nice and fresh. Right, so if we're going to investigate or study temperature changes, we probably need to talk about this in a different unit, or a different form other than degrees Celsius, even though I like degrees Celsius and not as much Fahrenheit, but we should come up with, or we should look at least considering some absolute value 0. Okay, so here's an experiment. Okay, so this is the setup. You have a hot plate, a thermometer attached to a retort stand, and a syringe. Okay, just all set up there. I performed this experiment once, kind of boring, hard to get exact values, so here's this graph for you. Okay, so volume on our y-axis and temperature on our x-axis. Now we have different points of data here. Okay, now at some temperature, 1, 2, 3, 4, 5, so at about 20 degrees, we have 25 mils. Then at 0 degrees, we have just below that, I'm going to say 24, 23. Now, what can happen is if you increase temperature further at 100, you have a certain volume measurement. And if we continue to take data points, eventually you will see that this equation, this line, not forget about the equation of line, but this line will touch the x-axis at a certain point, which means it can't go below this point. It'll stop right there. And in different scenarios, you will always end up at that x-intercept. So that value then ends up being, if you extrapolate this information, extending beyond your data set, your measurements, you then end up with a temperature that it's called absolute 0, that it can't go below. It's negative 273. I know we have decimals, that 273.15, if I recall correctly, and those decimal places are very, very, very important, but for us it's not as important. Okay, so we're going to just use negative 273. So if temperature then can't go below -273, there is a different scale we need to use, and that's called the temperature, or rather it's called the Kelvin temperature scale. Now, you don't say degrees Kelvin, you just say Kelvin, right? Now, think about what this means is gases, this suggests something interesting. I'm going to go back. This suggests that at this temperature, -273 degrees Celsius, the volume of a gas will be zero. That's really interesting, and scientists in different places in the world are actually studying this, studying what happens to matter at absolute zero, or at least very close to. It's very interesting, but not the focus of this lesson, right? So it goes to a zero volume, but not really, because there is mass there. But of course, there's more on that I'm not going to get into, and I really can't get into. But the space between them will approach, that's the word, approach zero, or maybe collide. That's for another lesson. All right, so at this point, all molecular movement stops. So atoms, particles, they stop vibrating, they stop moving. Okay, and this is called absolute zero. Absolute zero. There is no kinetic energy. Okay, so we can convert then between Kelvin and degrees Celsius, right? Don't say degrees Kelvin, it's just Kelvin. So Kelvin is equal to a degree Celsius plus 273. Okay? So to convert 62 degrees Celsius into Kelvin, all you then do is you take 62 degrees Celsius, 62 plus 273, and you get 335 Kelvin. Right, so 62 degrees Celsius is actually 335 Kelvin. Okay, a bit more practice. I'm going to skip over this. Not entirely though. I will do the first two with you, the first couple. So 0 degrees Celsius is, not really doing it with you. I'm just revealing the answers online or in this lesson, but this is posted online for you to work through. Okay, and 100 degrees Celsius is 373 Kelvin. Again, you're just adding that in the formula. Okay, so finally, back to Charles's law, as we were introduced to it, and then we talked about pressure. Okay, so we saw in our graph that we had a constant, right? Volume versus temperature created a constant, and mathematicians love that constant because you can create an equation of a line, right? And we saw that in the previous, in Boyle's law. So Charles's law just says that as the temperature of a gas increases, the volume increases. So as temperature increases, volume, why put that, but volume also increases. Okay, and it does so proportionally. Okay, that didn't prove to you, but it does so proportionally. So if you multiply temperature by 2, right, increasing it by 2, you will then also get the same doubling of volume. Okay, so our formula is then this. V1 over T1 is V2 over T2. Okay, so that's Charles's law. V1 over T1 is V2 over T2. And of course, our first couple of examples for that. So given this information, so a sample of gas occupies 3.5 liters right here at 300 Kelvin. Let's stick with Kelvin, so convert to Kelvin. What volume will it occupy at 200? So you've decreased temperature, you would expect volume then to also decrease. So here's all of our given information, and we're asked to solve for a second volume. Plug things into Charles's law, solve for your unknown V2, and you get 2.3. Okay, not too hard, a little bit of grade 9 math here. You're just rearranging, substituting and rearranging. Next, if a 1 liter balloon is heated to from 22 degrees Celsius to 100, right, so now you've done the opposite. You've increased temperature about approximately by 5. What will its new volume be? So we would expect this to be a greater volume. Okay, this is all of our given information. We're going to plug it into Charles's law, right? Solve for our unknown variable. We're determining what V2 is, and we get 1.26. Okay, now this would be a pretty good communication question. I just said that you are multiplying this by 5. Okay, but look, in reality, you have to convert this to Kelvin, right? Kelvin, we don't use Celsius, right? 22 degrees Celsius is 295 Kelvin. 100 degrees Celsius is 373 Kelvin. So you're not really multiplying it by 5. Not happening here. Okay, you're not multiplying it by 5, so you wouldn't expect this to be 5 liters, right? It's just over 1.25, so 1.26 liters. Okay, so interesting what's happening here. Not what you would expect because of the difference in units. Okay, probably a good source for a communication question. I have to remember that one. Okay, we're going to start wrapping things up now with Gay-Lussac's law. Here we look at this new law as describing the relationship between temperature and pressure. Temperature and pressure, and this is the law we get. It's instead of V1T1, right? Instead of V1T1, Charles's law. Now we're describing pressure versus temperature, and it turns out it is also linear. So we get linear, meaning, and I'll show you a graph in just a second, but it's a linear relationship. So P1 over T1 is equal to P2 over T2. Okay, you can cross multiply if you like to look at it like this. This to me, I understand what it's doing here, but this is just fine. So just use this one. This is perhaps a little more difficult to remember. Okay, so here it is. So in the summer, say we're looking at a tire here. In the summer, if the temperature goes up, which it usually does, so temperature goes up. So this way, pressure therefore in your tire also goes up, right? It's a linear relationship, directly proportional. So you want to just check to make sure that pressure isn't too high on those tires, especially on a really hot day, right? You want to make sure that you're driving safely. So check that tire pressure. This is an example, a picture of a tanker carried from somewhere south, traveling up north where it's colder. The pressure here must not have been regulated properly because what happens as it went from a very hot temperature somewhere in the south, where it was hotter or warmer, than to somewhere in the north where it was colder. So if temperature decreases, then what's going to happen to pressure here? Pressure will decrease. And look what happened to this big tanker as a result. It imploded. Not exploded, it imploded because pressure decreased so much. Okay, so first example, find the final pressure of a gas at 150 Kelvin, right? So it's already converted to Kelvin. If the pressure of the gas is 210 kilopascals at 120 Kelvin. Okay, so it's increased slightly by 30 Kelvin. Plug in your first situation, first scenario is 210 kilopascals, 120 Kelvin. Cross multiply, solve for P2, and you get 263 kilopascals. Okay, that should make sense because you have increased your temperature, so your pressure should also increase, and it does, to 263 kilopascals. So a little self-check there. And you're done. Watch this video online. It's a cheesy summary, but it's actually quite good. Okay, that's your home fun. I hope this helps.